Welcome to today's lecture. In the last class, we have seen vestigial sideband demodulation. We have seen coherent demodulation, and we have also seen what is the comparison between amplitude modulation techniques. What are all the amplitude modulation techniques we have discussed so far? Double sideband full carrier, double sideband suppressed carrier, single sideband suppressed carrier, and vestigial sideband. In all the four modulation techniques, we have compared bandwidth, transmission efficiency, and what are all the applications in it. These are the three parameters we have compared against all the four amplitude modulation techniques. In today's class, we are going to see what is transmitter and receiver in amplitude modulation. AM transmitter. In short form, I'll refer it as TR. What are the functions of transmitter? The first function is creating a generating or creating a carrier signal. Specified, it must be raised to the required power level. And the second one is processing the message signal and raising its power level. Processing the message signal or incoming signal or information signal, whichever term we use to refer the message, processing the message signal and also raising it to the required power level suitable for modulation, and modulating the carrier, and message signal, and also we need to raise its power level. So our basic operation in a transmitter is to, after modulation or before modulation, we have to raise the power level in order to reach the receiver, that is in order to cover the long range communication. And what are all the classifications available? Classifications are broadly, it can be classified based on frequency band. Based on the frequency band, it can be, our AM transmitter can be classified as medium wave transmitter, second short wave transmitter based on the frequency, okay, and then very high frequency transmitter or ultra high frequency transmitter. Medium wave transmitter, it covers the frequency range from 550 to 1650 kilohertz. Short wave band covers from 3 megahertz to 30 megahertz. It can be shortly referred as SW, MW, medium wave band, short wave band. This is based on the frequency band. Second one is based on the modulation. Based on the modulation, it can be classified as AM transmitter, second is FM transmitter. If our modulation is used for amplitude modulation, then it is AM transmitter. If our modulation is used for frequency modulation, then it is referred as FM. Then SSB. Fourth one is VSB. It's depending on our modulation, it is classified as amplitude modulation, frequency modulation transmitter, and single sideband modulation transmitter, and vestigial sideband modulation transmitter. And the fourth one is based on the service, whether it is used to, depending upon our application. So it can be named as broadcast transmitter when it is using for radio broadcasting. Second one is telephone, radio telephony or video telephony, telephone transmitters. And the third one is for radar transmitter. And the fourth one is for television transmitter. In broadcast transmitter, for audio signal, of frequencies from audio signal mostly covers up to 3 kilohertz. So we can either go for medium wave transmission or we can go for short wave transmission. Medium wave transmission covers frequency from 550 to 1650 kilohertz. Short wave band covers the frequencies from 3 megahertz to 30 megahertz. So in the medium wave propagation, we rely on ground wave. Ground wave propagation for the medium wave transmission, ground wave propagation. In for short wave, since we are having a frequency ranging from 3 megahertz to 30 megahertz, we have to go for skywave propagation. Since high ground wave propagation mostly affected or attenuated by the buildings, constructions, it is covering only the limited area. The service is only for the limited area, limited service area. It can cover only the limited area. But for sky propagation, for a different part of globe, for example, A is in a different part and B is in different part. Assume this is a globe. So short wave communication using a skywave propagation, it can cover long range. Long range communication is also possible using the short wave band. And for telephony, this is for audio broadcast transmission for audio. And what is the power level? We are using the medium wave and then short wave transmitter. If it is for ground wave, we have to go for medium wave. If it is for skywave propagation, we have to rely on short wave transmission. And the power level is from 1 kilowatt to 100 kilowatt. Power scale. For broadcast transmission. For telephony, it is for telephone transmission, it is many to one transmission or many to many transmission. But for broadcast, telephone is point to point transmission, point to point direct transmission, right? Therefore, here we have to rely on highly directional antenna. In order to obtain the maximum gain, we have to rely on highly directional antenna. And for the power scale, here we have to we can use only the few kilowatt power scale, because we have employed a highly directional antenna. We can use only few kilowatts of power scale. And for television, here we have audio as well as video. We can separately choose our modulation scheme. For audio, we can go for frequency modulation, and for video, we can go for vestigial sideband modulation. And this is based on the frequency band, this is based on the modulation, and this is based on the type of service or application. How our transmitter is employed in the real world. The fourth one is based on the power level. High power, low power, medium power and high power. If I have a power scale of less than 1 kilowatt, then it is referred as low power transmitter. If I have a transmitter of less than 5 kilowatt, then it is referred as medium transmitter. If I have a transmitter which is having a power scale greater than 5 kilowatt, then it is referred as high power transmitter. These are all the 4 important classifications of transmitter based on the criteria of frequency, based on the modulation criteria, based on the application and based on our power. Now we are going to see two types of modulation: low level modulation based on the power, low level modulation and high level modulation. The two classifications under power. We'll see one by one. What is low level modulation? Then move on our topic to high level modulation. So our first topic is going to be low level modulation. What is low level? When a linear amplifier is used to produce the required. Here in low level modulation, the information and the carrier wave are modulated before the carrier and message signal are amplified. That is, information signal and carrier signal are modulated and then amplified. That is, amplification is done in the last stage of the transmission. For example, we are having the RF carrier and we are having the modulating message signal, modulating signal or message signal. These are all the two input signals we are giving to the modulator. This is low level modulator. First our modulation is carried out, then amplification is, then comes the amplification part. Class B, linear. Mostly low level modulation involves linear amplifiers. RF, wideband amplifier. Then it will be transmitted to the antenna. To reach the receiver part. Here the power level will be low. To increase the power level, we have used the class B linear power amplifier to boost up the power level. Here predominantly we will employ either class A or class B type of power amplifiers. The power amplification stages are required to amplify the carrier as well as the modulating signal. It operates, since we have not amplified here, we are only amplifying the modulated output. So the power gain, low power gain and also efficiency will be low in case of low power level modulation. Power gain as well as efficiency, both will be low. Class A or class B type of linear amplifier is always employed in the amplifier stages. When we see in depth what are all the stages, this is our low level modulation stages. First is our stabilized RF oscillator. That is, in order to stabilize the frequency of the carrier signal, stabilize the carrier signal. Why we have to go for a frequency stabilization? In order to avoid the frequency drift in the carrier signal. We can employ crystal oscillator. Also we can employ LC oscillator. But crystal oscillator will always provide good stability. Local oscillator will provide weak stability in orders of stability criteria. And followed by a stabilized RF oscillator, we are using the class A buffer amplifier in order to remove the high frequency component and low frequency component. Only that particular frequency carrier frequency component must be fed to the one of the input as modulator. Again, this is our second modulating signal path. The modulating signal audio processing and filtering is done prior to the amplification. That is, we have to make all the signals sufficient to reach our modulation. Strong signals, in order to reach the sufficient level, strong signals can be processed with low gain. Weak signals can be processed with high gain. In order to make all the signals sufficient to reach the modulate part, then audio amplifier and filtering is processed by a class A or class B amplifier. Both the signals are fed to the modulator. Followed by a modulator, we have a series of amplifications. Linear amplifier followed by a power amplifier. These are all RF section. This is our buffer section, exciter section, followed by our power, RF power section. Then this is fed to the antenna. Here in the stabilized part, we have go for crystal oscillator or local oscillator, but in order to obtain the good stability, we have to rely on crystal oscillator. A crystal oscillator temperature has to be maintained in order to tune to the particular frequency, or else it will give adjacent channel selectivity, interference in your adjacent channel selectivity. Here the applications of low level modulation are: it is used for short range walkie-talkie, and second, it can be used for wireless intercoms. Which are all the applications having low power level we can employ our low power modulation, and for remote control units. This is a low level modulation. Now we are moving on topic to high level modulation. In high level modulation, amplification is done prior to the modulation. Amplification of carrier as well as amplification of modulating signal. Here modulating signal. Modulating signal is amplified by using the wideband amplifier. It is fed to the high level modulator as one of the input. Carrier signal, which is also amplified but by using the narrow band amplifier. Our carrier signals must be tuned to particular frequency FC, or else adjacent channel selectivity interference will get affected. Therefore, our modulating signal, which may be having a certain range, that must be amplified together, and both the signals are fed to the high level modulator. Then after a series of power amplifications, that is RF power amplifications, in the final stage it is fed to the antenna. This information is for a basic understanding, and the block diagram is given by. This is a high level modulation. Stabilized RF oscillator, we can use either a crystal oscillator or LC oscillator, followed by a class A RF amplifier and then class C RF power amplifier, which is fed to the high level modulator, and our A modulating signal. After making our signal, whether it may be a weak signal or a strong signal, we are making it as to reach the sufficient power level and fed to the class A or AB power amplifier, and then followed by the class B power amplifier. Both the stabilized carrier signal and stabilized modulating signal are amplified to the sufficient level, then fed to the high level modulator. In the previous case, in our low level modulation, after the modulation part, we have used the series of power amplifiers to increase the power level. But even high level modulation, carrier signal is separately boosted up, and then modulating signal is separately we boosted here. After boosting only, we are feeding it to the high level modulator. And this is here itself we are increasing the power level. So this is our low level modulation, and then this block diagram is for our high level modulation. Here we will see what is the comparison between low level modulation and high level modulation. Just now we have explained power level. Based on the three criteria we are going to classify, we are going to compare. Based on the power level, modulation is carried out at low power level. Modulation is carried out at low power level. Here modulation is carried out at high power level. And Based on the amplifier stages, it needs lesser amplifier stages, it needs more amplifier stages, because after modulation only we are going for power amplification. Here carrier is separately power amplified and then message signal is also separately amplified. Therefore, here we are in need of more amplifier stages. Power efficiency, here only linear amplifiers can be employed, class A, class B or class AB. Here non-linear amplifiers can also be employed. Here mostly class C amplifier is employed. Examples: linear, and here we can also employ non-linear amplifier. This is the comparison of low level and high level modulation. Next part, we are moving to AM receivers. In the AM transmitter, we have seen based on the power level, low level modulation as well as high level modulation. Similarly, in AM receiver, we are going to see what are the functions of AM receiver, and second we are going to see classification of AM receivers. Then we are going to see based on the configuration two types, tuned frequency and then super heterodyne receiver. Based on the function of the receiver is to pick up the modulated signal. And the second one is to amplify the picked up signal. Amplify the picked signal. And the third point is extract the message from or extract the message or recover the message signal using detector. And we have to raise the power level sufficient in order to excite the output transducer. Raise the power level sufficient. This is a function of AM receiver. And what are all the classifications? Again, similar to our AM transmitter classification, based on the modulation, it can be classified as AM receiver, FM receiver, SSB receiver, VSB receiver. Based on the frequency range, it can be classified as RF receiver, VHF receiver, microwave receiver. Based on the configuration, it can be classified as tuned radio frequency receiver. TRF, or it can be simply referred as TRF, and the second one is super heterodyne receiver. We are going to study TRF receiver and super heterodyne receiver. What is tuned radio frequency receiver? Or simply TRF. First we will see the block diagram of TRF and then we will go for the explanation. We will have a series of amplifier stages, first, second, up to n amplifiers, but all the amplifiers are tuned to the single frequency, that is why it is referred as ganged. We have a series of amplifier stages. After picking up the signal, it is applied to the first amplifier and then to the end stages of amplifier. Then the amplified signal is, we have studied picking the modulating signal using the antenna and amplifying the picked up signal, extract the message using the detector. Therefore, the amplifier stages is followed by the detector section to recover our message signal. An extracted message signal is raised to reach the sufficient power level. This is by using the audio amplifier, which is fed to the power amplifiers and it again fed to the output transducer. If it is an audio signal, it is fed to the speakers, loudspeaker. So this is a block diagram for tuned radio frequency receiver. Here we have used the word called ganged. Ganged in the sense tuning to same frequency. All of the amplifier stages are tuned to all the amplifier stages here. Here we have mentioned only 2 amplifiers. If at all we have more than 2 or we have n number of amplifier stages, all the amplifiers are tuned to same frequency. That is, all the amplifier stages are mechanically tied together, and if we set one frequency, then that will be automatically all the amplifiers reflected in all the amplifier stages. That is, the same frequency will be tuned in all the amplifier stages. That's why it is referred as ganged. Advantages in tuned radio frequency are: it is simple to design, it is inexpensive, and it has high sensitivity too. Disadvantages: first one is poor adjacent selectivity. Adjacent channel selectivity. When the receiver is tuned to the particular station, adjacent channels having frequency plus or minus 10 kHz which also be received, then which causes your adjacent channel to get interfered. That is why we are referring this tuned radio frequency as poor adjacent channel selectivity. And the second one is instability in RF amplifiers. All are tuned to exactly the same frequency, but the receiver is tuned to different station, means then it will go for instability in our RF amplifier section, and also it will go for uniform gain, non-uniform gain. Due to series of amplifier stages, the gain offering by the each amplifier stage may vary. Therefore, it results in this amplifier stage, series of amplifier stage will result in non-uniform gain. These are all the disadvantages of tuned radio frequency receiver. Therefore, we are going for the yet another receiver called super heterodyne receiver. Super heterodyne receiver. To overcome the disadvantages, that is poor channel selectivity, instability, we are going for the super heterodyne receiver. In most of our applications, we are seeing the super heterodyne receivers in our FM transmission and an AM broadcasting. We are using our super heterodyne receiver. First, we will see what is the block diagram for that, and then we will go for the explanation. After picking up the antenna signal from the antenna, it is fed to the RF amplifier. This is our block diagram for super heterodyne receiver. First, we will have an antenna which will pick up our modulated signal, followed by an RF amplifier which is fed to the mixture. This is our new stage which is differing from our tuned frequency. Earlier we have used only the series of amplifier stages. Here we are having a new stage called a mixture. What this mixture will do, here after picking our amplitude modulated signal, RF amplifier will have a frequency FC. This local oscillator is having a frequency of F0. Local oscillator frequency which will try to convert our incoming frequency into a same frequency, whatever may be the incoming frequency. By using the super heterodyne receiver, we are converting our frequency into same frequency. That is, the message bearing AM received signal, whatever may be its carrier frequency, is converted into an AM signal carrying the same message signal, called the intermediate frequency. This IFS stands for intermediate frequency. For example, our F0 is going to be FC plus this mixture FC plus FL. Therefore, in the mixture what it will do, local oscillator frequency will have FC plus IF, intermediate frequency. That is why we have referred it as FL. F0 is equal to FC plus FL. FC is our incoming modulated frequency and IF is intermediate frequency. Usually in audio transmitter, AM broadcasting receiver will have 455 kilohertz as intermediate frequency. Therefore, whatever may be our incoming frequency, this 455 kilohertz will be added and then this will be fed to the mixture. Therefore, the mixture will give two outputs. Sorry, this is our incoming frequency and this is our local oscillator frequency. This will be added together. Therefore, if for example assume our incoming frequency is 1000 kilohertz. Here our local oscillator frequency is 455 kilohertz. Therefore, the resultant here will be 1455 kilohertz. 1000 plus 455, therefore 1455 kilohertz. What will be the result of mixture? Mixture will give either FC, F0 plus FC, F0 minus FC. Since it is will sum the two signals and it will give the difference of two signals. For the rest of the stages, for the intermediate amplifier stages, for the detector, we are going to take only the different signal. F0 minus of FC will give, we know that what is F0. F0 is FC plus IF. What is then minus FC. So this two will cancel. Then you are going to transmit only the IF. Whatever may be my incoming frequency, if it is maybe 1000 or 2000 or 3000, this incoming carrier frequency will be added together with the intermediate frequency of 455. When these two signals are passing through the mixture, we are going to take only from this stage onwards, we are going to take forward only the different signal. The different signal will always going to have the intermediate frequency. Therefore, this amplification stages will going to handle only the intermediate frequency of 455 kilohertz. Instead of high frequency, which we have received 1000 kilohertz, in order to why we have reduced our frequency range from 1000 or whatever may be our incoming frequency to 455 kilohertz, that is in order to maintain the stability in our receiver section. F0 minus FC, therefore our this frequency is always 455 kilohertz. It is designed to have 3 dB bandwidth of 10 kilohertz to accommodate all frequencies in the AM signal. The mixture part, which is having a 3 dB bandwidth of 10 kilohertz plus or minus 10 kilohertz to accommodate the all side frequencies of the FM signal, because we know that in the amplitude modulated signal we have side frequencies, we have a carrier signal. If it is an direct conventional AM, we will have carrier signal as well as the lower side band and upper side band. If it is in case of a DSPAC, we will have the upper side band and lower side band alone. Therefore, our mixture should have a sufficient 3 dB bandwidth to accommodate plus or minus 10 kilohertz, so that all the side bands will be passed through the mixture circuit. Functions of RF amplifier is to ensure overall signal to noise ratio and also to give signal to noise ratio and also to give good image rejection, because high frequency component may also get accommodated or low frequency component may also will get affected. We have to tune to the particular frequency. Therefore, this our RF amplifier section must ensure high image rejection, frequency rejection, and it also ensures adjacent channel selectivity. These are all the functions of RF amplifier. And the local oscillator, it is LC oscillator, can also be used here. It is tuned to frequency called F0. F0 is FC plus of intermediate frequency. Intermediate frequency is always 455, which is predetermined one. This is important. So whatever may be the my incoming receiver frequency, local oscillator tracks in such a way that it will be greater than that of the 455 kilohertz. Therefore, incoming carrier frequency is 1000, then 1000 plus 445, it will result in 1445, and from this stage onwards only the different signal we are going to reject or eliminate or some signal, we are going to carry forward the different signal. This signal is going to have a frequency of 455 kilohertz. Then it is followed by the series of IF amplifiers which will give high gain and good sensitivity. These are all the functions of IF amplifier, which is followed by the detector extracts the message signal. Envelope detector can also be employed here to provide a linear operation and to avoid distortions, which is then again followed by the audio or voltage amplifiers and series of power amplifier. The demodulated output will be weak in power. Therefore, to boost up the power level, we are going for the audio or voltage amplifier section and power amplifier section, and also to minimize the distortion. This will be fed to the loudspeaker. Can we see this waveforms for it? So this is our incoming modulated signal. This will be fed to the this is our incoming signal on stage 1. This is fed to the RF amplifier. This is stage 2. So therefore, in stage 2, this signal will be amplified. This is a stage 2 result. Signal is drawn here only for our graphical representation, and the third stages are mixture. Here what we will do, we are going to mixing in 455 kilohertz intermediate frequency signal. Therefore, the resultant will be, in order to reduce the frequency range, here the amplitude must be maintained equal. This is our third stage mixing, and this is the resultant of our mixture, and it is fed to the IF local oscillator with the IF. This is our local oscillator. This is our IF carrier, the resultant signal, and the resultant signal is amplified using the IF amplifier stages. Amplifier stages is followed by the detector. Therefore, this is our third stage, local oscillator stage, third, fourth, fifth. This is our fifth stage, and followed by the sixth is our detector stage, seventh is audio. So sixth stage, we are going to get only the audio output, audio component, and which is again amplified by using the series of power amplifier. This is our seventh stage. This is the amplified audio component. This is the block diagram explanation, and this is the graphical how the spectrum is going to be time domain. This is not the spectrum, sorry, this is the time domain representation. How the time domain representation of the signal is changing for the when the signal is moving from one part of the stage, one part of the blocks to another part of the block. So successively when it moves on from the double sideband modulator wave from this antenna to and from this power section, which is fed to the after this part it is fed to the loudspeaker. So how we are recovering our amplitude signal, audio signal and our message signal, and then how this can be amplified. This is our diagrammatic explanation. Here our RF frequency is greater than the intermediate frequency. This intermediate frequency should always be greater than our information signal. This we have to keep in mind, because in audio signal mostly our information signal, audio signal will be having values from 3 kilohertz to 10 kilohertz, less than that. That is why we are always having a low intermediate frequency of 455 kilohertz. This is an important point which we must keep in mind for intermediate frequency. And the frequency range of RF is always greater than the intermediate frequency. RF we are mentioning as FC, always greater than the intermediate frequency. This intermediate frequency should always be less than that, greater than that of our information signal. That this is our FM. This is our FIF. And there are 4 parameters, important noise parameters in receiver parameters, which are sensitivity, second one is selectivity, the third one is fidelity, fourth one is noise figure. These are all the 4 important receiver parameters. Which need to be considered while designing the receiver. How much sensitivity it is offering, how much of selectivity it is giving, and what is the fidelity ratio, and what is the noise figure, signal to noise ratio, how much noise figure will be obtained. Normally it should be maintained between 5 to 10 dB. And this completes our unit 1.